Greetings, everybody. We're going to talk about uh, arithmetic operations and how we perform them on permutation groups by now introducing subtraction and division into the process. We had a short week last week that is, as we had a midterm on Wednesday. And on Monday, I talked about how to unify all four operations by way of permutation or shift arithmetic. So in this short video, I'll simply explain subtraction and division operations by way of permutation composition. Now, here is our addition table, the usual addition table that I've been using, mod 5 table. And in order to mentally think about subtraction, it may actually be helpful to think of this table, to transform this addition table to the subtraction table here, where we have written the two operands of the subtraction operation, column-wise and then row-wise this way. So we get to subtract, let's say 2 from 2, we get a 0. We subtract 3 from 2, we get a -1, but that's equal to +4. So all the entries are actually positive here because those are our entries in mod 5, but we think of these positive quantities also as negative quantities, like in this example I've given you. 2 minus 3 is equal to -1, that's equal to 4. Or likewise 1 minus 3 is equal to -2, and that's equal to 3. So now we need to transform this into shifts, these actually operands. And in the case of addition, we shifted things down. We're shifting cyclically the wires down. To get, for example, operand 2, we would simply shift input 0 2 places. Shift it down. Now, in the case of subtraction, we're going to shift things up. We go in the opposite direction. And again, we'll do this cyclically. So if I want to get 4 into into one of these networks that I'm going to implement this on, instead of like shifting 4 places down, I actually shift up a place. And the reason that I like to think about this as shifting things up, wires up, is because I don't want to make this conversion explicitly when I see a negative sign in front of an operand. I want to basically use that negative sign along with the amount of the operand that I'm subtracting without making this transformation by, as we normally do, by complementing the bits of the operand and adding 1 to it, as in 2's complement arithmetic. So here is an example that hopefully explains this. So here's 2 minus 3. If I were to really carry this in 2's complement arithmetic, I would simply think of this minus 3 as I should say complement arithmetic, because I'm just doing mod 5 complementation here. And that minus 3 is the same as 2, so I get to add 2 to 2 to get 4. And now, instead of like thinking this as plus 2, I would focus on the first expression and simply enter these two numbers into these two boxes here. So 2, as before, is going to be simply shifting something down by 2 places. No shift, 1 shift, and 2 shift is what I do. For this minus 3, I'm going to shift up 3 places. So here's, if I didn't shift, and if I shift once, I would have come down here. Sorry. And if I shifted second time, I would have come down here. And if I shifted third time, I would have been here. And that's what I end up doing. So no shift, 1 shift, 2 shift, and 3 shift. And now that I've created the two maps, then I get to simply compose the two, whatever technology I have, but it's electrical, optical, any other technology. This composition will take place all by itself, as a result of which I end up taking 0 to 4, and that's what tells me what the result is going to be as before. And so these things are composed in here, multiplied together, at the end of which 0 goes to 4. And that's my simply subtraction here. And I do this by completely bypassing this transformation, where I end up basically transforming 3 into 2 because it's a negative 3. I don't really do this physically. All I do is look at the negative sign and then look at what this number is and then shift things up 3 places as opposed to shift things down. That's what it is. Okay. Now I could do a little more about this reading process here. As I mentioned in class, when we get a result here, whether it's addition or subtraction, we kind of have to search where 0 is at to know what result we really have obtained. Here, 0 happens to be here, so I say, well, obviously my result is 0. But then 0 could be here, it could be there, it could be at any one of these output ports. And that means I have to search, I have to sense where 0 is. And that will add to this computation. In order to avoid this, we could actually work with the inverses of these maps. So here's how I do it. If I were to add, and I'm just giving an addition example here, this is just an addition case, the subtraction is performed the same way. If I were to add 2 to 4, instead of using p squared and p4, I actually use p minus 2 and p minus 4. I'm just working with the inverses, which will then give me p minus 1. So this multiplication simplifies things, because now this map P inverse would tell me what actually comes to 0. And that would then be enough for me to tell what result I actually get by looking at this output 0 location, because I'm actually looking at P inverse, meaning where 0 would be mapped from. That would reveal that. So now I take these two maps and I simply write P minus 2 and P minus 4 into these two boxes. Now P minus 2 is the same as like P3. You can think of that. And that is this map here. You could also have done this, by the way, by going up 2 places. In other words, once you think of this as inverse map, you could still use 2, but instead of like going down, you can go up 2 places. And that will take you right here. No place, 1 place, 2 place. And the same is true for this one. So going 4 places down, like this one, you can actually end up going, in this example, yeah, instead of going 4 places down, you actually end up going 1 place down. Or 4 places up. Let me just say it this way. Instead of going down 1 place, you could actually go 4 places up, which will take you back here. So no place, 1 place, 2 place, 2nd place, and then 3rd place. So this is where you end up coming down with 0 because of this 4. It's just simple fact that 4 is the same as like 1, and that's what this happens. But you could do this by going up 4 places instead of coming down 1 place. And that is to say that we only look at these two operands. We never really think about these -2 and -4 in that regard. We don't physically make these changes, but simply view these as upshifts and downshifts. Like in this case, I'm only looking at these as upshifts. So, excuse me. So now we have the 2 maps created. Again, I go ahead and multiply them. And then when I do, I realize that 1 ends up coming to 0. And this is where 0 is mapped from. And that's all I need. This is what this map tells me. And of course, that tells me that the result of this operation must be equal to 1. Let me just do this right here. It's equal to here, actually, 1. And that coincides with this. So the difference between this and the other approach is that here I have to search to see where 0 is at. But here I will always look at this output, which is 0 output 0, to see what result I get in the end, this composition. And it simplifies it because I don't really have to search around to see where 0 is. I'm just looking at physically wire 0, whatever I sense out of that place, is what I get. That's, in this case, 1. So one other thing is left, that's multiplication, or division rather, and I should say modulo division. And so modulo division is the same way that we did subtraction. We're going to do modulo division, so we create the multiplication table as before. This time, of course, we don't put the 0 in, and then we write the division table. Division table is worked out the same way. Every one of these numbers have an inverse, like 2 has, the inverse of 2 is equal to 3 because they multiply to 1. Inverse of 4 is itself, inverse of 1 is itself. So these are the inverses. And an operand divided by another operand simply means a mod 5 in this case, an operand multiplied by the inverse of the second operand. So let's say that I take 3 and then divide it by 2. I'm actually thinking about multiplying 3 by the inverse of 2, which happens to be 3. So 3 times 3 is actually 9, and then mod 5 is 4. That's what I get here. So 3 divided by 2 is the same as 3 times 2 inverse, and that is equal to 3 times 3, and that is mod 5 is equal to 4. That's how I do this. And of course, as before, we use 2 as a generator for both tables, and that's how these numbers are represented. Actually, this is fixed once we fix the multiplication, so these numbers are still going to be represented by powers of 2. This is kind of critical because we will then take that generator to the generator of the permutation group, and then because both of them are cyclic, they're going to carry the same computation in 2 different forms. So here's modulo 5 division, I should say. And to carry out this division, I simply think of the corresponding permutation group and write the entries as such. So as you can see, I just simply take these entries, and the numbers become the powers of my generator, which is equal to, in this case, P on this side. It is 2 over here, and whatever power that I have here, whatever entries I have here, I kind of power them with this, with these numbers. And so, and that's again, that just comes from the fact that these numbers, not really these numbers, but the powers that will get me to these entries. So 2 is of course 2 to the 1, and then 1 is p to the 4, which is equal to identity, and then 4 is actually p squared, and 3 is p cubed, and that's how these numbers are obtained. And so now the only thing that remains is to perform this operation, which is really no different than what we did before. This time, of course, our network size has gone down by 1 because we don't really use 5 inputs, but only 4. But this is still our 0, 1, 2, 3 network. That is to say, our entries are, we could actually have written this as 1, 2, 3, 4 as well. But that makes no difference. So we write 0, 1, 2, 3, and then we first realize 2, which is actually, in this case, 2 to the 1 is 1 shift. And then 4 is, the inverse of 4 is actually 4, that is 2 squared. So we shift 2 places, and then we multiply. We compose the 2 maps, and we do. 0 ends up coming to 3, and that means that our result is actually 3, because 0 ends up coming to 3. I haven't given an example here where I use the inverse maps, but you could do the same. That's the same process. It's just to explain to you here that, the division is carried out much the same way as multiplication, by simply transforming the 2 operands into these shift networks or shift diagrams, and then carrying out the composition to read off the quotient in this case. So I guess the main point of this video is that all 4 operations of modulo arithmetic can be carried out by shifts in these networks that we call, I guess, permutation networks, permutation switches. and all the carry computations are completely out the door, and this simplifies, or I should say unifies all 4 operations into shift operations, which is the shift computation. So what would be next? We'll discuss division-free modulo arithmetic and Montgomery algorithm. When I say division-free, whenever you compute things, you have to do a mod operation in modulo arithmetic, obviously, and that mod operation typically means you've got to get the remainder. To get the remainder out of a computation, you must perform a division. And so what Montgomery algorithm does, it actually performs all of these things in binary, and either by truncating bits or by shifting bits, you get all the computations in modulo domain. That's going to happen next week. So until then, take care, and I'll see you in class.